Now, let me start by introducing the topic of this talk. I will talk about the rigidity of the isoperimetric inequality of the negative affective dimension on with Riemannian manifolds. And maybe you're not familiar with some words in the title like isoperimetric inequality on affective dimension with manifolds. I would give the definition later on my talk. But as you know, the isoperimetric inequalities is a classical topic in geometry, and it studies the lower bound of the parameter of sets in terms of the volumes. And in modern geometric analysis, this topic is very interesting because it connects geometry of lower curvature bound with other theories in mathematics. In this talk, I will give a story of isoperimetric inequalities in the connection with the L1 optimal transpose L at the subspectral inequalities. And the main theorem in my research asserts that in a West manifold with positive Ricci curvature bound of the negative effective dimension n, which is smaller than -1, the equality in the isoperimetric inequality implies that the manifold must be isometric to the warp product of the one-dimensional Euclidean space with a hyperplane, and the warping function is a hyperbolic cosine function. Here, the one-dimensional Euclidean space is equipped with a hyperbolic cosine method, and the isoperimetric minimizers could be half space. Here, the warp product on the results could be defined as the product of a Riemannian manifold with an open interval, and the product metric is warped by a positive warping function f. And now, let me introduce about the concept of wedge manifold. A wedge Riemannian manifold will be a structure of a complete connected boundaryless Riemannian manifold, and it's equipped with the Riemannian metric G and a Borel measure. We also call it the manifold with density. Here, the density function of the measure structure C is assumed to be smooth. The setting of wedge manifold is very interesting, and it naturally arises in limit spaces of unwedged manifold in Gromov-Hausdorff sense, and it is related to the study of conformal deformation of Riemannian matrix. And in wedged Riemannian manifold, I study the isoperimetric inequalities. The isoperimetric inequality in wedged manifold estimate the Minkowski exterior boundary and the volume with respect to the density. We define the perimeter of a set as the Minkowski exterior boundary, and the isoperimetric profile of a volume parameter theta is the infimum of the Minkowski boundary among the Borel sets of fixed volume. And the isoperimetric inequality in wedge manifolds state that the isoperimetric profile with the volume theta is bounded from below by a functional of theta depend on the Ricci curvature bound K, the diameter bound D, and the dimension bound N. And IK and D, and the functional IK and D theta is also the isoperimetric profile of one-dimensional Borel space given by Emmanuel Millmans. And in this study, I studied the behavior of the manifold when the inequality becomes equality. As you can see on the isoperimetric inequality, the wedge Ricci curvature bound collision appeared. And in the setting of weight Riemannian manifolds and metric measure spec, a new theory of comparison geometry under weight-rigid curvature bound has been studied intensively in the last decades. Rigid curvature plays an important role in geometric analysis on Riemannian manifold because its bound can be used to control the geometric quantity distortion as well as the global topological information. Furthermore, rigid curvature can be used to measure the distortion of optimal transport of sets between flat and curved space. And in the definition of weight-rigid curvatures, the appearance of density function were inspired by the study of the Markov diffusion operator in gamma calculus by Bakary and his collaborator. And note that in the definition, rigidity stands for the rigid curvature on unweighted manifold, and the density appear on the additional part. And we write rig n greater than k if we have the inequality holds for all unit vector v. Recently, the development on the curvature dimension correction CDKN in optimal transport theory has set new light on the theory of curvature bound for weight manifold. The parameter k is interpreted as a lower bound for Ricci curvature, and the parameter n is interpreted as the upper bound of the dimension, and we call it the effective dimension. And the curvature dimension constant CDKN is equivalent to the weight-rigid curvature bound rig n greater than k. For positive curvature bound, or when k is a positive, if the effective dimension n is positive, the manifolds are compact. But for negative effective dimension n, in general, the manifold is non-compact. It's interesting that even on positive curvature bound, we have the non-compact space. And that turned out to be a weak theory for weight-rigid curvature bound when the effective dimension is negative, because it's the weakest condition among the range of n. This might sound strange due to the interpretation of n as a upper dimension bound, but it's covered interesting examples such as the hyperbolic space. And in this research, I studied the case when n is negative. I would recall some basic fact about the setting of weight manifold. And first, I will introduce the weight Laplacian. On weight manifolds, the Laplacian is also modified such that we have the green formula holds even with the new integral associated with the new volume measures. The study of the first non-zero eigenvalue with respect to the weight Laplacian is connected to the isoperimetric inequality, and I would explain that connection later. One more important estimate on weight manifold is the Boltzmann inequality, and Boltzmann and on unweighted manifold, Boltzmann formula plays a key role in the study of geometric inequality under lower rigid curvature bound on Riemannian manifold. And we are able to generalize the Boltzmann formula into the setting of weight manifold. And in Boltzmann inequalities, the function u is often chosen so that the gradient on the Laplacian is simple enough to compute. Therefore, we would apply it to the eigenfunction or hidden function and so on. When we choose use as the eigenfunction of the first non-zero eigenvalue of the weight Laplacian, we obtain the subspectral gap inequality and equivalently the sub-Poincare inequality. Here, this is the subspectral gap inequality. It states that if a manifold satisfies the positive rigid curvature bound for negative effective dimension n and the finite volume, then the first non-zero eigenvalue lambda 1 of the weight Laplacian is bounded from below by the constant kn over n minus 1. And Equivalently, this constant and the constant kn over n minus 1 is also the sub-constant of the Poincare inequality on West manifold. Here we give an example of the one-dimensional spec that satisfies the equality on the subspectral gap. This is a one-dimensional spec introduced by Millman when he studied the isoperimetric inequality. We take M1 as the M1 as a West manifold with one-dimensional Euclidean spec and standard metric, and it's equipped with the hyperbolic cosine measures. And here the Ricci curvature is equal to k everywhere. And for n smaller than minus 1, the first non-zero eigenvalues extend the lower bound kn over n minus 1. And the hyperbolic cosine function is the associated eigenfunction with respect to lambda 1, with respect to the constant kn over n minus 1. The fact that M1 satisfies the rigidity of subspectral gap as well as the isoperimetric inequality inspire me to connect two inequalities via the needle decomposition technique. Before going into detail, let me show the result of the rigidity of the spectral gap. In my previous research, I found that if a manifold of dimension n satisfying the positive Ricci curvature bound for the effective dimension n smaller than minus 1 of finite volume, and the manifold is of finite volume, and we assume furthermore the first non-zero eigenvalues of the Laplacian extend the lower bound kn over n minus 1, then for high-dimensional spec, M must be isometric to the warp product of the one Euclidean spec with the hyperplane, and the warping function is a hyperbolic cosine function. And if we decompose the measures of the wedge manifold, we have that the one-dimensional Euclidean spec is equipped with the hyperbolic cosine measures, and the submanifold sigma satisfy another Ricci curvature bound. And for one-dimensional spec, the wave manifold must be isometric to the modal spec M1 up to a constant multiplication of the measures. Now let me move to the main part. Let me first introduce other rigidity results on other ends of effective dimension n. For positive n, Cavaletti and Molino used Massimo diameter theorem and needle decomposition to obtain that the equality in isoperimetric inequality imply that the manifold is necessarily isometric to the spherical suspension. And for infinity n, Frank Morgan used the geometric measure theory technique to obtain the equality case on isoperimetric inequality hold if and only if the manifold is isometric to the product space of the Gaussian spec. And here the submanifold sigma also satisfy another Ricci curvature bound. In my research, when n is negative, the non-compactness of n and the weaker condition of Ricci curvature bound arise some problem, so that we cannot use the maximal diameter argument as well as the convexity. So I decided to use the needle decomposition and mix it with the Riemann analysis on hyperbolic space. But first, let me show you the result on one-dimensional case. The rigidity on the one-dimensional scale is achieved by one-dimensional analysis based on the proof of Millman on the isoperimetric inequality, and the result shows that if a manifold of dimension 1 satisfying the positively curvature bound for n smaller than -1, and we also suppose we also normalize the volume to be 1, and we assume furthermore that there exists a volume parameter theta 0 satisfy such that the isoperimetric profile extends the lower bound. Then the manifold must be isometric to the one-dimensional model spec M1. And the calculating on the lemma 11 make sure that we can remove the diameter bound. Moreover, if a set of volume theta satisfy the Minkowski boundary equal to the lower bound of the isoperimetric profile, then this set must be a half spec, must be an one-dimensional half spec. And my approach to generalize that result to higher dimensional is to use the needle decomposition on Riemannian manifolds, and it is a localization technique introduced by Klatak to reduce high-dimensional problem into one-dimensional problem while preserving the rigid curvature bound. In my research, I used needle decomposition induced from the L1 optimal transport of the isoperimetric minimizer to the complement set, and the particle which move along the heuristic in the needle decomposition through the boundary of the isoperimetric minimizer. And this heuristic is called the transport ray. We first define the transport ray of a Lipschitz function U, and U who satisfy a distant line property on the ray in the maximal sense on definition 13. And we would foliate a manifold into a collection of transport rays of the Lipschitz function U, so that the rigid curvature bound remains on its transport ray. And Klatak stated his celebrated needle decomposition and follow. And if a West manifold satisfies the rigid curvature bound, and we have F is unintegrable with zero mean, then there exists a one Lipschitz function U that we call the guiding function. Partition Q on M, and it is a collection of needles, and a probability measures on Q, as well as the family of probability measures Vi on the element of Q, such that and we can decompose the volume of A by the partition Q. And secondly, almost all element of Q is minimizing heuristic and transport ray associated with the guiding function U. And the element of Q is either a singleton or it is a one-dimensional manifold satisfies the rigid curvature bound. And for almost every element in Q, the mean of F remains 0. With the needle decomposition technique, I could give an alternative proof of the isoperimetric inequality. We take the needle decomposition associated with the function f and the difference of the indicator function of a set A with its volume. By foliating the manifold along this needle decomposition, we obtain that the boundary measure of A is larger than the integral of the boundary of the foliated path of A in all over the needles. But why the volume is equal? Hence, the isoperimetric inequality is proved provided the one-dimensional inequality holds. Now we use this proof to achieve the main theorem as follows. If a Waite manifold of higher dimension than 1, satisfying the weight-rigid curvature barrel for effective dimension n smaller than -1, and we normalize the volume to be 1, we assume that there exists a volume parameter theta 0 such that the equality on the isoperimetric inequality holds. Then the manifold must be isometric to the warp product, similar to the case of subspectral gap inequality. And the isoperimetric minimizer must be a half spec in an appropriate sense. That's I will describe it on the proof. Here's the key point is that we use the guiding function on the needle decomposition on the proof of isoperimetric inequality to construct the eigenfunction on subspectral gap inequality, and we found out the rigidity of the two inequality would imply the same warp sweeping phenomenon. Here is the sketch of my proof. First, we take the needle decomposition associated with an isoperimetric minimizer, and we take the function f to be the difference of the indicator function and the volume. And in step 2, we take v as the hyperbolic sign of the guiding function with respect to the needle decomposition on step 1. And by one-dimensional analysis, we found that we satisfy the equality of the Subspectral inequality on one-dimensional needle. And in step 3, we're taking the integration over all the needle, and we found that we satisfy the equality in the Subspectral inequality on the whole M. And hence it becomes the eigenfunction for lambda 1. And we obtain the similar splitting phenomenon in the rigidity of subspectral gap inequality. This is the key step because in general it's very difficult to take the integration over the needle, and the usage of the guiding function plays a crucial role for this talk. Here I give a simple calculation on one-dimensional needle to show the equality of subspectral inequality on one-dimensional space, and it's very easy to verify by yourself. It is a step 3 that we take the integral on over the needle to show the equality of subspectral inequality on high-dimensional space, and it's also very simple to verify. And now we investigate the shape of the isoperimetric minimizers. And one-dimensional analysis shows that the isoperimetric minimizers must be one-dimensional half space. We assume when we foliate the minimizer into needle, the foliated path has two inverse directions, and both have the lux measures Q1 and Q2. By recalculating the Minkowski boundary, we found that there is a contradiction since the boundary measure became too large. Hence, all the needle has the same direction of the isoperimetric minimizers, and it must have a shape of half spec in the sense of a product of a one-dimensional half spec with a submanifold. Now we move to the discussion and remark of this research. The interesting point here is the connection between isoperimetric minimizer and Poincare inequality via the needle decomposition, and it would open a way to study other isoperimetric type inequalities in Waite manifold by connecting it with some functional inequality. If you want to read more about the needle decomposition technique in Waite manifold, you could try to read the Isoperimetric Inequalities in Compact Metric Space by Cavaletti Molino, The Rigidity of Logarithmic Subspectral Gap Inequalities by Ota Takasu, The Quantitative Bakri-Leduc Inequality by me and Professor Ota. And I thank you for the listening, and don't hesitate to ask me about my talk.